In 1989, my then mid-teenage self watched the television coverage of Voyager 2's pass of the planet Neptune. Being that age, I was ecstatic to see actual close-up images of Neptune in a way humans had never seen before. This planet before that time had been a vague blue dot in telescopes, and this was the days before Hubble. Voyager 2 had delivered, as Voyager 1 had done at Jupiter, Saturn, and Titan. There was much elation, both in the public and scientific community, over a triumph of a pair of spacecraft that had been launched in 1977, complete with a televised party with Chuck Berry performing, one of the performers on the famous gold record. The spacecraft would go on and survive until today, 25 years further than that Neptune flyby. Voyager 2 is still doing active science in the interstellar medium, and Voyager 1, at least right now, is sending signals but no useful data, but there's still hope of fixing it. These beautiful legacy missions to investigate the gas giants and ice giants of the solar system now ply interstellar space, bearing their gold record messages from humanity to anyone that may someday find them. My guest today is deeply involved in recovering Voyager 1 and keeping these missions going to measure the environment outside of the solar system for hopefully years to come.
You have fallen into Event Horizon with John Michael Gaudier. In today's episode, John is joined by Dr. Linda J. Spilker. Dr. Linda Spilker is a JPL Fellow, Senior Research Scientist and Planetary Scientist at NASA's Jet Propulsion Laboratory, who has participated in NASA and international planetary missions for over 45 years. She is currently serving as the Voyager Project Scientist. Her mission roles have grown to encompass mission leadership, as well as design, planning, operation, and scientific data analysis. Prior to Voyager, she was the Cassini Project Scientist, leading a team of over 300 international scientists to maximize the scientific return of the Cassini mission within the cost and schedule. She worked in a science role on the Cassini project for 30 years and was co-investigator with the Cassini Composite Infrared Spectrometer team. She led the Sears Ring team, focusing on thermal infrared studies and modeling of Saturn's rings to address questions of the ring's origin and evolution. Remember to subscribe to Event Horizon so you never miss an episode.
Dr. Linda Spilker, welcome to the program.
Thank you very much, John. It's a pleasure to be here.
Now, Doctor, you have been involved with planetary science for many years, and myself as a space enthusiast have as well since the 1980s with Voyager. And one thing that stuck in my memory was the circumstances around the pass of Neptune and the surprises of Neptune and seeing that world back in 1989 for the first time, which before then, Neptune had just been this dot in a telescope. Can't even see it with the naked eye, but there it was, this beautiful blue world with clouds and a spot somewhat similar to Jupiter. And it really captivated my then teenage imagination. What was that like, being a scientist at that time? What was that like, and what is it like now, still working with both of the Voyager spacecraft?
Well, that Neptune flyby was so amazing. It was the first time a spacecraft, Voyager 2, had flown by Neptune. And for me, as a ring scientist, I was so fascinated by Neptune's rings because they were arcs of material. They were not the complete rings that we saw at Saturn and at Uranus. And so to try and understand those very puzzling arcs was truly amazing. And then to get a close-up view of Neptune's large moon Triton and to see this surface kind of looking, part of it looked like cantaloupe terrain, and actually seeing tiny geysers going off at the south pole of Triton, and just the amazement and so many new discoveries that came not just of the planet, but of the rings and the moons in that system as well. And that was true for me for all of the planetary flybys. I had the rare privilege to be part of the Jupiter, Saturn, Uranus, and Neptune flybys. And such incredible science, in a sense, rewriting the textbooks that we had at that time about what we knew about the planets and their moons and their rings. And today is no less exciting. It isn't as colorful and visual as what we had with the planetary flybys, but we're in a totally new place in interstellar space. And that's something Voyager's good at, making discoveries and going to new places. So after flying across the solar system, crossing a boundary called the heliopause, the boundary between the sun's influence and interstellar space, we've been flying now with Voyager 1 for more than a decade, studying what it's like in that space between the stars, looking at the particles and the fields and making measurements to help us better understand and put in context our own solar system and the stars in our galaxy.
The heliopause is an interesting word. What exactly is the heliopause, and why do we use that as a demarcation line of the end of the sun's influence? In a certain context anyway.
Right. It's not so much the end of the sun's influence, but it's just a boundary where the solar wind has reached out far enough. There's this wind that comes from the sun, and it's now balanced by the interstellar wind. And that balance point creates a boundary that we call the heliopause. The heliopause isn't a static boundary. It actually moves in and out because the solar wind varies as the solar cycle varies. So that wind from the sun varies, pushing the boundary in and out just a little bit. And that interstellar wind is generated from supernova explosions from stars as they've aged and exploded and have blown out these large bubbles of gas. So in a sense, our heliopause is nested between these bubbles created by these supernova explosions and perhaps even space in between those as well.
And so it's sort of like a sail, and sometimes it billows, sometimes it doesn't, and sometimes there's calms. And so with the Voyager spacecraft, at least Voyager 1, sometimes you see the heliopause, sometimes you don't, as it moves in and out. Is that a good characterization?
Yeah, the heliopause moves just a small amount. The Voyagers now are well past it. In fact, Voyager 1 is at 160 astronomical units away using the Sun-Earth distance as 1 AU. So it's quite far away. We didn't see necessarily multiple crossings of the heliopause as we went across it. It moves very slowly because the solar cycle has a very slow variation as well. There's still events, we call them shocks or pressure fronts, events that come out from the sun. Maybe you have a coronal mass ejection, some large event that just puts out a tremendous amount of particles and energy, and that can actually go through the heliopause and make itself felt out in interstellar space. And so along the way, Voyager has witnessed these shocks and pressure fronts as we go, and we're wondering, where does that moment occur where we no longer see this influence from the sun? And it may go out quite some distance, actually.
That's interesting because, that you can see an event on the sun, and presumably with great delay, you can see it in the outer, very, very outer solar system, if you can even call it that at that point. So what is the delay like? In other words, you see the sun shoot off a flare, and how long does it take for Voyager to actually see that far out?
It can take many years for that event to reach the Voyagers. To kind of give you an idea of how far away they are, at the speed of light, it takes a signal, almost a light day, 22 and a half hours to reach all the way from the Earth out to Voyager. And so that's traveling at the speed of light. And so, of course, it takes these events from the sun that are traveling much more slowly, a longer time to reach out to each Voyager. So in a sense, the events from the sun that we're seeing with Voyager 1 or with Voyager 2 are actually events in the past from the sun that we have seen propagate outward and into interstellar space.
Can you see things with the instrumentation on the Voyager spacecraft that look like the activities of other stars? In other words, do you see events blips or whatever, very tiny blips that might indicate that a star nearby has had some sort of eruption?
We don't really have the instrumentation to look for events coming from other stars. There might be evidence as we go further along or look at the data more closely, some kind of an event. But in general, the Voyagers are not used for sort of that astronomical study of the stars.
What's their health like? How is Voyager 1 and how is Voyager 2?
Well, Voyager 1 experienced a problem that started in mid-November, and it's currently not sending back useful data. We get data back just about every day from each Voyager spacecraft, and we looked this day in November, and we could see the carrier or the tone, the signal coming from the spacecraft, and it was sending back basically some random pattern of zeros and ones, but not what we'd call useful telemetry or science data or engineering data. It could be perhaps there was a bit flip somewhere in one of the computers, could be something else, but we don't have any useful information to help us decode it. So, but on the other hand, Voyager 2 is still healthy, sending back useful science and engineering data just about every day.
What instruments are you still using on these spacecraft? Well, when you can communicate with them, is it just magnetometers and things like that? And what would the condition? I mean, could you turn on a camera still with Voyager 2 and take another solar system photograph? You know, the famous pale blue dot photograph. I mean, or is it just too far gone at this point to be able to power that up?
You're correct. Yeah, I mean, the pale blue dot image is one of my very favorite images to actually take Voyager 1 and look back and take this wonderful mosaic of the planets in our solar system. That's fantastic. But you're right, we don't have enough power any longer on Voyager 1 or Voyager 2 to power the cameras or any of the instruments that were on what we call the scan platform, that optical remote sensing platform, looking from the UV into the far infrared. And so we can't really do that. But the instruments that are still operating, of course, we have the magnetometer on both spacecraft, something we call the plasma wave spectrometer that helps us look at these shocks and pressure fronts coming from the sun. Voyager 2, the plasma spectrometer is still operating. It's not operating any longer on Voyager 1. We also have a cosmic ray spectrometer that helps us measure the energy and abundance and composition of the cosmic rays. And we found that heliopause is really a boundary that's protecting us from a significant fraction of those really highly energetic cosmic ray particles, mostly particles of helium and hydrogen atoms that have been accelerated. And then finally, we have a low energy charged particle instrument that looks over a broad spectrum of energies at what we're seeing actually sensing. So you can see we're physically sensing what is around the spacecraft with the set of the instruments that we have remaining that work on Voyager.
A different spacecraft that was in every way just as important, the Cassini spacecraft, and you worked extensively with that at, Saturn. And Saturn is an unusual planet, to say the least, because of its beautiful ring system, but also the fact that it's a gas giant and in resonance with Jupiter and very, very important to the solar system, the formation of the solar system as we know it, and Earth. And that mission, though, that highly successful mission that lasted for many years, how did that come about? And how does it relate to the Voyager missions? In other words, as a sort of development of the Voyager missions, how did Cassini come about?
Well, Cassini is really and truly a child of Voyager, because in the 1980 and 1981 Voyager flybys of Saturn, one of the key questions that Voyager hoped to answer was to see what the surface of Saturn's large moon Titan looked like. We knew Titan had this thick, dense atmosphere. We really wanted to peer down and see what the surface looked like. But with the instruments on board Voyager, we could not see through that photochemical haze. The cameras couldn't see through it. And so we didn't know what the surface looked like. So almost immediately after the two Voyager flybys, some scientists from the United States and Europe began lobbying their space agencies for another mission to go back to Saturn with an orbiter this time that would carry a probe that could go into Titan's atmosphere and land on Titan's surface, and to really probe that question that had been left unanswered by Voyager. And so all of that interest from the science community then led to the Cassini mission, and it allowed development of the NASA built the Cassini spacecraft, and the European Space Agency built the Titan probe called Huygens, named after the discoverer of Titan. And so we sent this pair to the Saturn system, and the Huygens probe did successfully land on the surface of Titan, found an absolutely amazing world. We also carried a radar instrument on the orbiter that could probe through the clouds and the haze, and we were better at our filter selection on our cameras so we could see the surface of Titan. And we found an amazing place. We found a world where methane plays the role that water plays here on the Earth. It could be a gas or a liquid or even an ice. And so we saw methane flowing in rivers on Titan. and filling North Polar seas, and just an incredible, very, very interesting world, a prebiotic world, perhaps something like the early Earth might have looked like, only it's just very, very cold, and that any water is actually the water ice on Titan forms sort of the bedrock or the rock on Titan. So that was just an incredible, incredible set of findings by the Cassini spacecraft. And I think if you thought about Cassini, another star was a moon called Enceladus, much smaller than Titan itself. This tiny moon Enceladus actually had jets of ice and gas that were blasting material into space. A lot of these tiny particles formed Saturn's E-ring. But even more important, Enceladus had a liquid water ocean underneath its icy crust. And we think that this ocean might harbor the ingredients for life. And Cassini actually had a chance to fly through these jets coming from the South Pole of Enceladus 7 times and sample and get the composition of the material. And that really leads us to think that perhaps there's really a possibility for an ocean world, in this case, to have life.
2 different moons that each have their own liquids, hydrocarbons at Titan and water at Enceladus. And either one could, in principle anyway, and I mean, it would take a long time to prove this, but in principle, either one of them could support some type of life. And particularly Titan would be very low temperature life. And I find that really intriguing, that it's almost like a laboratory, the Saturn system, because you've got 2 different liquid worlds that are very different from each other.
That's right. That's right. It is possible that you could have some sort of life in the methane seas. Here you have all these hydrocarbons on Titan, and that's a very interesting possibility.
What do we do in the future to further explore Titan? And perhaps more importantly, how do we shield Titan from contaminating it with our type of life and actually see if it has indigenous microbes or something like that in those methane lakes?
Right. Well, we have a mission to go back to Titan. It's called Dragonfly. It's going to be an octocopter, actually, that will fly through the atmosphere of Titan and land at various places. It's not targeted to go close to the seas that are at the North Polar region of Titan, but it's going to be taking samples, sort of vacuuming up samples of the surface, taking it into the spacecraft and making measurements of that. So it'll be a very interesting mission. I think it might be a quadcopter mission, but it's still the idea of actually sending something that can fly in the atmosphere of Titan. I think it's very exciting.
It doesn't get more exciting than that. Just the idea of, we're doing it on Mars, but just a quadcopter on Titan. But let me ask you this. The mystery of Titan is deeper than what we've discussed so far. In other words, how does it even have an atmosphere? Being that small, you would normally think that something like that in the solar system would look like the moon. It would just be this dry, atmosphereless place, but it's not. It's got a thick atmosphere. How is it doing that?
Yeah, that's a very interesting question, because Jupiter has a large moon, Ganymede. It's about the same size as Titan, maybe a little bit bigger. It doesn't have a thick atmosphere like this. And so that is a very interesting question. Did something impact Titan? Is it just releasing the methane they think that's trapped in this material called clathrate? Clathrate forms like a cage that holds the methane molecule and then can be released with time. We do know this, though. The methane in Titan's atmosphere, it's light. It goes, it goes far away from Titan's center. UV photons hit it and break it apart. And that's what actually helps grow the longer and longer chains of hydrocarbons. But once that source of methane is gone from Titan, then the atmosphere could possibly collapse, because it's really the methane working like a greenhouse gas that's keeping everything warm enough to support an atmosphere of that size. So it's a very interesting question.
It is, and it's so different from the rest of the moons of the solar system. They're all different. You could invoke Ganymede, that, not much atmosphere, but look what's under the surface, potentially.
Absolutely. There might be a liquid water ocean. It's got a magnetic field. Yeah.
It has a magnetic field.
It's amazing. They all have their unique personalities and character. Who would have thought this tiny moon Enceladus, a tenth the size of Titan, would have a liquid water ocean underneath its icy crust?
It does, and one of the weird things about Enceladus is it looks different. You would normally think it would be a very close relative to Europa, but it's not. Why is Europa, the cracks in Europa, why do they have colors, yet Enceladus, they're bluish? And what is coming up from the depths of those ice shell moons that makes them so different from each other when they should be similar?
Yep, a very interesting question. There's also a big difference in size between Europa and Enceladus. And we know that a lot of Enceladus's surface is very young because much of the material that comes out of the jets coming from the South Pole actually falls back and is coating the surface of Enceladus. And that's why it's so bright white and icy. And that was one of the puzzles for Voyager. Here's this bright white icy moon. It's in the center of this ring, that they named the E-ring. How could it be so bright and white and pristine looking? And then with Cassini's discovery of the jets at the South Pole, that let us know that now we had a reason why it was so bright. And with Voyager, it's interesting. The South Pole was in darkness when Voyager flew by Enceladus and took its pictures of Enceladus, or perhaps it would have been Voyager that would have seen those jets.
The other thing, too, is that Enceladus has a profound effect on Saturn's rings. In other words, it's shepherding and creating one of the rings. So that outflow of material, outflow of water, is actually affecting the entire Saturn system, right?
That's correct. It's coating at least one side of every moon in the system, that is out, well away from Saturn's rings, coating with E-ring particles. And we're sort of seeing the signature of that water throughout the Saturn system.
So wait a minute, you actually see that with the other moons of Saturn? You see the snow from Enceladus?
In a sense, the two sides look different, and we attribute that to being coated with material because we know those E-ring particles are so tiny that they're influenced by the pressure from the sun, solar pressure. They're influenced if they get charged by the magnetic field, and they actually are just spreading throughout the system. And then they get swept up by those moons as they orbit in the Saturn system.
Now, from Jupiter is a very active, violent world, giant, just almost scary in a way if you look at it. Yet Saturn is quiescent, but yet these are two similar planets. They're both gas giants. What is the radiation environment like at Saturn versus Jupiter, which we know Jupiter has this radiation torus, and it's absolutely horrible. It's throwing out radio and doing all kinds of things. What's Saturn like? And it almost seems like it's more quiescent. Why is that?
Yeah, Saturn, the rings actually work as basically a radiation shield, or like a blanket, that in order to generate radiation belts, you need particles that spiral along magnetic field lines that flow from the North Pole to the South Pole. And at Saturn, those rings are in the way. So any particles that try and get charged and spiral on the field lines get blocked by Saturn's rings. And so it gives it a very benign environment when it comes to radiation. In the case of Jupiter, Jupiter does have a ring system, but it's very tenuous. And so the particles can spiral back and forth along those magnetic field lines. And Jupiter, the biggest planet in the solar system, it has the biggest magnetic field. It's a very harsh radiation environment. And so that's the difference. If Jupiter had a nice thick blanket, a nice thick plane of rings like Saturn does, they're only about maybe on average, 10 feet thick or so, but there's enough particles there to actually block the formation of dense radiation belts like you have at Jupiter.
Now, that's an interesting thought because we don't really know how old Saturn's ring system is or why it's there or how long it's going to last. So could we end up, if say that ring system dissipates one way or another, falls into the planet or whatever, what happens to Saturn if it doesn't have a ring system? Does it turn into something closer to Jupiter?
That's a really good question. In fact, there's evidence from Cassini. Cassini actually could measure the mass of Saturn's rings because its final orbits were actually in between the main rings and the top of Saturn's atmosphere. And by getting that mass, we think that the Saturn's rings are maybe young, maybe only a few 100 million years old, maybe 400 million years old at the most. And so that's much younger than the 4.5 billion year age of the solar system. And the rings are slowly being eroded away by micrometeoroid bombardments and things like that. So perhaps only last maybe a few hundreds of millions of years more. We're not really sure, but there could be a time. In fact, maybe there was a time before the dinosaurs were around where Saturn didn't have rings. The rings formed Perhaps there was an impact or a comet was torn apart or an impact into one of the other moons that actually formed the ring system, and then they may erode and be gone. And then Saturn will have more intense radiation belts, that's for sure. But since Saturn is not as large as Jupiter, they probably will not be as intense as Jupiter. But the rings really and truly do act as a shield.
That's absolutely amazing. So, all right, you remember back in the 90s when Jupiter got hit by a comet, and that which was you could even see that in an 8-inch telescope, and I did, and you could see as it rotated around, you could see those dots, the scars. So, could Jupiter, in principle, rip apart a comet and end up with a giant ring system in the far future, just like Saturn has currently?
It certainly is possible. There's probably a lot less material for that in the system for that to happen. But that's certainly possible. You just have to have the right kind of orbital conditions. You have to maybe put it into a more gentle orbit from sort of an eccentric orbit into a more gentle orbit, and then perhaps capture some of that material. Another thought about the evolution of Saturn's rings is maybe there was a large moon, Titan-sized moon. It had maybe differentiated, and it was actually in the early days when there's a lot of dust and gas in the Saturn system, maybe it slowly wandered into close to Saturn. And so maybe that nucleus with all the heavy material went into Saturn, and then that icy material formed a ring. So perhaps it could have formed from a moon, from a comet, a lot of interesting ways you could form a ring.
It's been floated in the literature that maybe Enceladus might not be that old, as opposed to some of the normal bodies of the solar system in 4.6 billion years, and that it might not quite be that old. Do you know anything about that?
Well, it's an interesting idea in looking at how you might form the moons in the various systems. With Saturn with its rings, there's one thought that perhaps what you do is you spin off, you sort of collect at the edge of Saturn's main rings these moonlets, if you will, and maybe they sort of spin off one by one and maybe kind of come together and grow the moons over time. And so that's one thought or one idea for how you might get the moons in the Saturn system. Dating without having a lot of craters, usually craters are one way that we often will age date a surface by looking at how heavily cratered and doing crater counting and lots of things like that we've done for our moon. But in Enceladus, there just aren't a lot of craters to count. So you have to look perhaps at the neighboring moons around it. But even those, it's interesting. Some of those may have been modified through interior processes as well. And for me, that's interesting because, not only did Voyager fly by Jupiter and Saturn, but Uranus and Neptune as well. And we got a glimpse of the moons in those systems. But the Uranian system in particular is very interesting. Miranda looking like it was torn apart and thrown back together. And there's some moons in that system, Ariel in particular, out from Miranda. You wonder if there might be ocean worlds in the Uranian system as well. And so there's a chance to go back. A mission is in the very earliest thought stages to go back with an orbiter to Uranus and perhaps with a probe as well, maybe to send into Uranus to study an ice giant up close and study its moons and rings and the planet as well. That I'd love to go back to Uranus.
I would too. I think that we don't spend enough time thinking about the ice giants. And they're hard to get to, but we did it with Voyager. And it's time to go back and take a closer look because there is some weird stuff going on. In particular, Triton with those geysers that Voyager 2. I mean, what's going on there? That's such an alien thing, yet in some ways weirdly familiar to Earth, just a different liquid. So there is really interesting stuff in the outer solar system, and I think it's time to go back.
Oh, I agree completely. I mean, Triton, we think, is a captured object. It's in a retrograde orbit, maybe a captured Kuiper Belt object. And it'd be very interesting just from that aspect of it to study Triton and compare it perhaps to Pluto. But so many interesting things to see. And in the case of Uranus and Neptune, we've just had one chance to go there. And I agree, it's time to go back.
And we almost didn't go. Do you remember, in the very, very early days of Voyager, it wasn't the grand tour quite yet. It was just Richard Nixon said, well, let's do two of them, Jupiter and Saturn, but not the other two, which we ended up doing because it was obviously convenient and the right thing to do. But it almost didn't happen. We could still be living in a time where we hadn't even seen a close-up picture of Neptune.
Yeah, that's right. That's right. Although I would say that even though the initial mission was 4 years duration, just Jupiter and Saturn, The navigators, the people putting together the orbits, very carefully planned that to make the opportunity be available to go on to Uranus and Neptune. Another part of that story that's very interesting is that the Voyager 1 flyby of Titan in particular had to be successful because we could have retargeted Voyager 2 to follow a very similar trajectory to Voyager 1 and also fly close to Titan had something gone wrong with the Voyager 1 flyby. But fortunately, everything went as planned. And that gave us then the chance to say, okay, now we're going to use Saturn to slingshot us on out to Uranus and Neptune.
That was a very unique juxtaposition of the solar system to be able to do all of those gravity assists and hit those planets like that. But we did sacrifice Voyager 1. What was the circumstances? And I know the answer, obviously Titan, but what was the reason to say, okay, Voyager 1 needs to go here and not go to Neptune or Uranus, but Voyager 2 we will. What was the circumstances of that?
Yeah, I think you're right. The decision was that Titan was a very high priority. Also, we didn't know, we'd never sent something that far away to last quite that long. And so we're saying, let's get Titan. At Saturn. We know the mission can last that long. Let's get Titan. But just sort of having in our back pocket Voyager 2 then to send out to Uranus and Neptune. And if you look back at some of the early studies that were done, there were actually ideas for multiple spacecraft such that you could have 2 flybys of all of the planets from Jupiter on out, and including, a Pluto flyby. So then as part of that descope, as you said, down to just Jupiter and Saturn, we actually lost additional spacecraft that we could have also sent, Voyager 3, Voyager 4, could have sent to multiple flybys of some of these other planets.
Now, fixing Voyager 1, can we save it?
Well, we've put together a tiger team of experts made up of people from the project and people outside the project, and they're taking a careful look, in particular, going back and looking at all of the old documentation and memos, and also past anomalies, past events that have happened to see if they can get some clues for what might be happening on Voyager 1, since we're not getting any information back. But it's really a lot like an archaeological dig. You have to go in and you think about it, a lot of these memos and things are paper copies that were scanned in. Sometimes the paper copies are still around. And so you have to pore over those and try and understand what had happened at that time. And there's not a lot of the early experts left who built the spacecraft who can help us sort of decode what's going on. So it's really sort of a detective problem. But we're sending commands up. We're trying things. We're basically making changes in the hardware. You can imagine if your computer gets screen freezes or something, you turn the computer on and off. We're doing some of that with the hardware and trying to observe what happens when we make these sorts of changes. We call them power on resets. And so we're learning more each week as we make these commands and send them up. And so the hope is that, yes, we'll be able to figure out just what we need to do in order to get Voyager 1 back and to send us science data back once again. Voyager was really in a fascinating place. We'd seen something, it's nicknamed Pressure Front 2. It's been lasting since 2020. It's not your typical shock or pressure front. It didn't decay and go back to its normal values. The magnetic field jumped up. The electron plasma density jumped up, and we'd like to see, go back and see, is it still there? Is this something unique to interstellar space rather than an effect from the sun, or is it something else that the sun did and that we've got to try and figure out? So there's still a lot for Voyager 1 to do, and having a pair of spacecraft, kind of like, can think of stereo vision of interstellar space, probing 2 different places, going out 2 different ways. So it would really be nice to get Voyager 1 back. And I'm optimistic. I think we've got a lot of really smart people working the problem, and that we'll be able to get Voyager 1 back.
It's not dead, though. You're still getting carrier signal, right?
That's right. We still get a carrier signal, and there's even on what they call the subcarrier, there's even information in there. It's just not useful information, this repetitive pattern of zeros and ones, or what they call string of symbol data. It's just not making sense. We think that's very likely the flight data system. That's the computer that usually takes the information from the science instruments and from the engineering subsystems, packages it up, and then sends it down. And so we think maybe something went awry, maybe in the processor itself, maybe there was a bit that was flipped in the memory. And so we're focusing in more and more on that particular system. There's 3 sets of computers on Voyager, that flight data system, sort of a command and control computer, and then an articulation and attitude control computer. And each of those is redundant, and they have redundant memories. And so we're trying to, make use of that fact as we now look more carefully at the flight data system.
Which is the further out? In other words, after all those gravity assists and motion and movement, moving through the solar system, which one is more distant, Voyager 1 or 2?
Well, actually, it's Voyager 1. You'd think, well, Voyager 1 only flew by Jupiter and Saturn, but the key really was Jupiter. That Voyager 1 came within 5 Jupiter radii of Jupiter, and that really gave it a lot of additional energy. And so it's actually moving faster than its Voyager 2 twin, which passed Jupiter about 10 Jupiter radii. And even though it had 4 planetary flybys, it's going a little bit more slowly, and so it's a little bit further behind.
Now, what is the delay time? In other words, you send a command to, Voyager 1. How long does it take to get there, and how long does it take it to even respond when it can?
Yeah, it's over 22 hours now for a command to get to Voyager 1. And so it takes another 22 hours, so almost 2 days to come back before we know. It's sort of like saying hello and waiting 2 days for someone to say hello back to you. And so it's far enough away now that it's a long wait, even at the speed of light.
What's the signal strength like at this point? In other words, is it a really difficult signal to pick up when you're trying to listen for a communication from a Voyager spacecraft that distant, and given the fact that these old spacecraft are losing voltage?
Right. It's a very, very faint signal that's coming back from the Voyagers. I don't have an exact number, but it's very, very faint. I mean, the total power coming out of that antenna is like maybe the equivalent to the power of your light bulb in your refrigerator or something. But we have these huge antennas. You can think huge ears on the Earth. Some of them are 70 meters in size, and they're spaced around the Earth at 3 different complexes. And so we can use those to listen for the data to come back. In fact, Voyager 1, sometimes it's been recording information about 1 frame a week of high rate data for the plasma wave spectrometer. And then a couple times a year, we send it back. And then we have to use the 70 meter plus 4 of the smaller 34s all put together, working together to pick up a very faint signal that's coming back now from the tape recorder. The digital tape recorder on Voyager 1 is still working. And its data rate is a little bit higher than we usually get. So we have to use all of the antennas, what we call arrayed together, to get that signal back. So it's just really amazing what we can do.
Digital tape recorder, is that actually a mechanical, something analogous to like an 8-track that's still working?
You're exactly right. 8-track tape recorder. The tape physically moves across the head, and we record on a track, and then we play the track back. And that's exactly right. That's how we got back all those pictures of the planets that we flew by early in the mission. It could hold, I think, all of like 100 pictures. And then we had to turn and play them back. But yes, an 8-track digital tape recorder.
Unbelievable. And then it's still working.
And it's still working.
In deep space. The humans have put an 8-track tape recorder that still works after almost 50 years into interstellar space.
Pretty amazing. Yes.
Did you know Carl Sagan back in the day?
I didn't know him well, but I would see him. He would be there for every one of the planetary flybys. And he was always very gracious and interested in talking about his ideas. Everyone was so interested in sharing their ideas about what we might see and what it all might mean. And he had his show at the time. And he was really the one that was key in getting back that pale blue dot image, really convincing NASA that we needed to take Voyager 1 before the cameras were turned off. So on Valentine's Day, we turned the cameras and took one last series of images, of which that pale blue dot of Earth is one of them. So yeah, he was really remarkable. He was also very proud at helping us get Chuck Berry after the Neptune flyby. Chuck Berry actually came to JPL, and he played Johnny Be Good to the flight team. And it was a great party, a great celebration of the success of Voyager to that point.
They actually televised that. I remember it. in 1989 where Chuck Berry played Voyager Be Good, I guess he said, or something similar to
Yeah,
that.
could be. That's right. Yeah, yeah.
And yeah, it was interesting because
Great.
I wish that we would do television coverage of stuff like that today. Like with New Horizons, and obviously we live in a very different internet world now where you can watch whatever you want. But back then, that was an event. The flyby of Neptune was an event, and I sort of miss those days in a certain sense. What do you think?
Yeah, I know what you mean. I miss those days as well because I remember through the Voyager flybys, and in particular for Neptune, we had TV cameras set up in the cafeteria and all these different places where you could just stop and watch the pictures come back one by one. And in those days, at Neptune, it seemed like forever to read back a frame, but you could stand there and line by line watch as each picture would come back. And I remember just sitting there, especially in awe for the Triton pictures that came back. They came back in the middle of the night, and all of us were just gathered around watching line by line as this new world was revealed for the first time. Very exciting way to watch and participate as part of it.
Though that did get repeated many years later with you remember the first pictures from I forget which lander it was, one of the rovers. It was either Spirit or Opportunity, and it was coming back, and it was pretty clear that it landed in a crater that was in sedimentary rock, I mean, sedimentary rock right there.
Right, right. Yes.
So what's in the future? How much longer are we going to have the Voyagers before the plutonium runs dry, so to speak? It's just too far gone. What can we expect?
Yeah, I think the plutonium, the power is probably really the limiting factor, where we have about 4 watts less of power on each Voyager each year. We've been slowly turning off the various subsystems that are redundant or parts that we can, and in probably 4 or 5 more years, we'll have to one by one start turning off the science instruments as well until we're down to just one or two, but that we can make it potentially into the 2030s, so barring other things that happen with aging spacecraft. We have the power problem, which also translates into the spacecraft itself as getting colder. And so as the components get colder, that could be perhaps more stressful for them. They're colder, they're older, and we could perhaps see, also more of these anomalies, these single event upsets perhaps from cosmic rays as the time goes along. But if everything goes perfectly, it is possible with the current power that we have to get out into the 2030s with at least one, maybe two instruments still operating. One amazing story from Voyager is the fact that in order to conserve power, we needed to turn off the heaters to 3 instruments that are actually partway. They're sticky. They're outside the spacecraft on this boom that goes out to the scan platform. And so we turned off the heaters on these instruments, 3 on Voyager 2 and 2 on Voyager 1. And we figured as we turned the heaters off, the temperatures would drop so low. They dropped like 70 Celsius, far below whatever we'd ever tested or expected them to work. And yet every single instrument kept working. In fact, the detectors, being colder, in some cases actually got more sensitive and worked better. And we've had to recalibrate some of the science data. So just an amazing, here's this old hardware. You turn off a heater and it gets super cold, and this instruments still keep working and still sending back data.
Just to put this into perspective, what was the design life of the Voyager spacecraft? In other words, when we first sent them out, how long were they supposed to last?
Yeah, the main mission we call the prime mission was 4 years to get 2 flybys of Jupiter and 2 of Saturn. But of course, the engineers were designing and putting together Voyager. They used the very best parts they could find and tried to make everything that's really important redundant, 2 of everything. So if one thing broke, we'd have a backup. So on the engineering side, pretty much everything is redundant. On the science side, there's just one of each instrument. You don't have duplicates of the instruments or any parts of the instrument. But the engineering side, they were very careful about that. Duplicate sets of thrusters, the duplicate computers. So we did not have a duplicate tape recorder, though, because that was primarily for science that we used the tape recorder.
No backup for the 8-track.
No.
All right, Dr. Spilker, thank you for joining us today. And I'm still excited for the Voyager missions, and I hope we can get Voyager 1 back.
Yes, me too. I'm hopeful that we've found a way so many times in the past to overcome anomalies that I think we will find a way to overcome this one as well.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.